Добрый день. Здравствуйте.
Я заметила, что все...
В конце лекции.
Да, заболелась. Не очень сложно. Консультация с да, онлайн. Не, понятно, что все равно. Между нашими. А у нас придет
Okay, dear students, I think that we can start. So today I will try to speak without the microphone. So please, if you feel that it will be not very convenient, please tell me, but it will be more or less better for me to discuss the ideas that we will elaborate today. Yeah, could you please call our students, our mates as well, and then we will start. Yes, Polina? Yeah, we will do it before the writing the quiz, okay? So, okay, dear students, please sit down. And today I will structure my talk in the following way. There will be no slides. There will be just a Jamboard with explanations. Please follow them. And also you can write the notes on yourself in order to structure the information. Well, by the way, Irina, do you hear me well, or it's better to take the microphone? Yeah, Irina. Oh, great, thank you. So we are speaking about the hypothesis testing. So it is hypothesis testing. So I suppose that somebody will also join us in Zoom. And let me check that the recording is going on. Yes. Okay, it is hypothesis testing. Previous time we have started to discuss it. Well, actually, let me introduce some other new functionality of Jamboard hypothesis testing. Yeah, so for this time, we have spoken a lot about different objects, their population and sample. So we have our population, so it can be our students, our citizens of the city, or something else, and we have sample, our sample. In statistics, we are very interested in analyzing the properties of the sample according to the population. So we need to understand whether it is representative sample and if there are any changes after some transformation with this sample. So like it was with the students that were drinking coffee during ordinary period of study and during the exam session. So when this exam session has started, it means that a new treatment has become, and there were some hypotheses that students drink coffee more often than usually. So that's why we tried to elaborate a bit more on this concept previous time. But let's do it in a more detailed way today. So we will pose hypothesis. So just a reminder, the plural form of hypothesis, so let me just click it here, is ES, not just IS. It is a Greek word. That's why we have this singular form IS in the end, and the plural form is ES. So we will pose hypothesis about our samples, well, let it be not about. On samples relating to population. From which the samples were taken. Is it clear? Okay, thanks. So let's just move on. So we need to make some inference. So it's called inference, our goal. make inference What is inference? It is conclusion or insights about our samples. Make inference about the samples. So that's why the chapter that we are studying right now is called inference statistics. Inference statistics. And in this field, a great number of topics is devoted to different tests, statistical tests on our samples according to our population. About samples. Okay. So now let's see the following example. We have the following numbers there. Here is our sample X. We have 2, 4, 6, 8. Some values in our sample. We have 4 observables and our mean is equal 5. Now we will, let's suppose that it is our population just from 4 observables, and now we will construct all possible samples. Let's write it. Let's create all possible samples from population X of, with size equals to. Size equals to. Okay, yeah, so I'm just trying to make these new technologies work. So let's suppose that it is equals to not just -2, because yeah, I have some problem here. Yeah, now it is equals to, let's suppose it. So how many different variations, and also there is detail that we can repeat the same value twice. So there can be in our sample 2 twice, then 4 twice time, and 6 twice time. And it's said that we will have such combinations equals 2 to the power of 4. Whereas 2 it's our size of sample, and 4 it's our the size of our population. So the size of our population equals 4. So we need to make all possible samples of the size 2. So there will be 2 to the power of 4. So totally there will be 16 different samples. So Jamboard doesn't want to make this equal sign. So let's just once again try to. Well, you know, there will be sometimes switching off of the projector. I don't know why it's happening, but it will return to the normal conditions. So please don't worry. So yeah, it is, well, it's not very good. So let's just use, yeah, this form equals 16. So does everyone understand what we're doing right now? Yeah, we're constructing 16 samples. So we have done it earlier. So let's just let me just import all possible samples. And no, let me just try once again. Here we are. So here are all possible samples. Yes, you also see it. So what is the first column? It's just our number of sample or just ID. Let's call it ID. Then we have our first value in our sample, then second value in our sample, and the last column, it's our mean. It's our mean. So in sample, we have the notation of mean like M capital. So returning to the previous population, we see that the mean of population equals 5. Now let's see how many samples here are also have the mean equals 5. So here we have mean equals 5, also here, here, and here. So that means that we have 4.16 out of 16 samples. It is 1.4 or our 0.25. 25% of all generated samples that we are taking from our initial sample have the same mean as it was in our population. In this case, we will say that our sample is ideally represent the initial population. So indeed, we have the same μ's as it was here in our population. And we constructed all possible samples, and our values also can be repeated, like here 2, 2, and 4, 4, and so on. And in this example, we have taken 1 out of 4 samples. What this example stands for? So in our real life, when we working with sample, we also want to understand whether it represents the population and in which extent, because there is always some error with which we take this sample from our population, and in data analysis we want to understand with which level of error we are taking these samples. So let's just go further. So actually what we have constructed here is called the distribution of distribution. So let me just take this. Distribution. So something goes wrong. Distribution of samples means. Samples means the last column. We are looking at the last column. It is our mu of all our samples. We have 16 mu's, and we can also plot the distribution of this samples means. Well, right now it is just the frequency table, but you can also visualize it like the histogram of samples means. And this distribution of sample means will be also the central part in our hypothesis testing. Why? Because we'll work with testing on our means. So now let's see the following. Well, it's also called the mathematical expectation of the sample mean that we have taken here. So when we have constructed these samples, samples means distribution, That's it called samples means distribution. We have here some other terms. So here our actually we want to calculate now the mean of sample means. So if we return to this slide, it's just like deepen into the next level. So we have created 16 samples and calculated the mean of each sample. Yeah. Now let's calculate the mean of samples means. So it will be some number here. So we calculate, sum up all these means and then divide by the number of means, and then we will take the means of sample means. So, and in this part, it's called the mathematical expectation of sample means, but actually we will be more interested in the standard deviation. So in here, we have our standard deviation, and it will be calculated in some other. Let me just take not the pen, but marker. So it will be calculated in the following way. It will be sigma divided by square root of n, and it will be called standard error of mean. Standard error. Let me just. So it's called standard error of mean. In shortened, it will be calculated as SEM. So here is our standard error of mean. Or SEM. So why do we need to divide by the square root of n? When we have obtained all our samples, calculate their means, we also need to make this adjustment according to the size of the mean. So let me just briefly recap for those who has come just right now. So we are working in the Poisson hypothesis, and we want to make some inference about our samples, inference statistics. So, and before we start, we need to see the following example. We are, well, sorry, actually you don't see it. We creating all possible samples from our initial population. Let's just take it for simplicity for values in this population. And also we are assuming that we can take every value the same twice. So it will be 2 2s, 2 4s, 2 6s, and so on. So then we will construct all possible samples that we have here, and we will calculate their means. So for each sample, we will calculate the mean, and it will help us to understand which our constructed sample will be the most representative one, those sample that has the same mean as it was in the population that were taken with red circles. They will represent ideally our distribution. There will be totally 1 out of 4 possible samples in our distribution. Then we're taking distribution of samples means and calculate now the mean of samples means. Среднее выборочных средних. And then we calculate the standard error of mean, which is calculated by the following formula. Now let's see how. Yes, Vasily?
I don't quite understand this formula. So to my mind, this like G equals to G divided by the whole n.
Mhm.
However, I understand that these are not G's, but they seem to be equal. X equals to X divided by 4.
Mhm.
What do the past questions then?
Yeah, let me just give you the following example. I'll just answer both of your questions. So, so it's not G, it's sigma, Greek letter sigma. Let's just write the transliteration, sigma. Our standard deviation. And let's suppose that we have two different situations. We have two samples. The first has n equals 4 observations. Another has n equals 16 observations. Now let's calculate. Well, we need also to add this subscript m, which indicates that we are calculating the standard error of means, not just standard deviation.
Why sigma?
It is it's just an example. We take some two samples in which the standard deviation is the same, but different sizes of these samples. And now we want to calculate this measure, which is called standard error of mean for the first sample. So what it will be? It will be 12 divided by square root of 4. So it is 12 divided by 2. So it is 6.
And n is the amount of entries in the sample.
Yeah, n equals the size or number of entries in our sample. And for the second example, we need to divide 12 by square root of 16. It will be 12 divided by 4, and it is equal to 3.
Sigma. What does this mean? What does sigma mean? What does it mean?
Sigma is standard deviation.
I see.
Yeah, and you see in this following example, we have the same standard deviation for the first sample and for the second sample of means with the size of entries equals 4 and 16. But their standard deviation, standard error of mean is different in 2 times. So for the first example, our standard error of mean sigma m equals 6. For the second sample, it's twice less. It equals 3. Yes, Polina?
Just a question. If we have the standard error of mean and standard.
It's actually, yeah, returning to the very first thing that we want to achieve. We want to construct such sample that will as much as better represent our population. In order to find this sample that ideally represents our population, we need to calculate a new measure, not just standard deviation, but standard error of mean. It has a two-step procedure. Firstly, we calculating. So here we just in detail discussed that we need to construct the all possible samples that we can take from our population, and then we calculate this distribution of samples means. And then the standard error of mean indicates us by which extent we are mistaken in our sample when we're assuming that some inference or some insights about this sample corresponds to the population. Let me just proceed. The very first part about hypothesis testing is very abstract always. But we need to go through this step, and then we will do this all calculations, all these algorithms, then you will see all the schema. But it will be much better if you will take in your head that we are trying to make the following. We make our sample ideally represent the population with some error. That's why we're calculating the standard error of means. And the second thing, when our sample has made some changes, well, for example, with students who drinking coffee, when the exam session has started, we want to understand whether the level of drinking coffee is also changing or not. So that's why inference statistics or hypothesis testing will help us.
The standard error is the worst is sample.
The higher standard error of mean, yeah, that means that we mistaken higher in our sample that was generated from our population. But actually, this measure will be additional one. It's we can't derive to final conclusion only depending on this standard error of mean. We will see how we can use it in other formulas. So let me just briefly give you an example from our course that was recorded a couple of years ago, I suppose. So, and group of Japanese and Korean will see. So note this actually. Let me just take another screenshot. So it will be here. So familiar teacher, it is Tatiana Ragovich from Japanese 21 and Korean 21 group should be familiar with her. So, well, actually you don't see it, sorry. Now you see it. So here's the screenshot from our online course that was recorded, but it was for Russian students, Russian speaking students, but you're also Russian speaking. Let's elaborate a bit more on this example. So we have also some sample, well, actually not sample, population of 5 different values, 12, 3, 6, 6, 9. We have calculated its mean, it's 7.2. So the mean, it's the summation of all entries divided by the size of population. Now we want to construct all possible samples equals 3. But in this example, we won't repeat each value several times. That means there will be no sample where it will be 3 times 12 or 3 times 3. But there can be 2 times 6 because there are actually here 2 6s in our population. So totally there will be 10 different samples here. Then we are calculating the mean that we are taking of these samples means. And we will find that there are 3 samples that have the same mean as it was in approximately in population. But you see in population it was 7.2, but the mean 7 for the first, second, and for the 10th sample will be the closest mean to our initial mean. So here's our distribution of samples means. We have 5 different values, 5, 6, 7, 8, 9 that were calculated before. We have calculated the standard error of mean by the formula that we have discussed, and it equals, well, it depends on the size of our sample. If it is equals 4, the size of entries, then it will be 6 SEM. If it is SEM equals with n equals 16, then it will be 3, like in the example that I have shown you.
Ask the samples those for which the sample error is minimum.
Sorry, could you please repeat?
Ask the best samples those for which the error is minimum. Like the less SEM, the better the sample is, or differential.
So if you mean if the SEM is closer to 0, can we generate such samples?
I mean, the closer is 0, the better the sample.
Yes. Yeah. So the higher, the lower SEM, standard error of mean, then it's better represent our initial population. Okay, let's move further if there are no questions. So now let's repeat the algorithm that we have discussed last week. So first of all, we need to pose some hypothesis. So we have claimed that this hypothesis should be written like this. It is our null hypothesis, and also we have our alternative hypothesis. So in statistics, you can find different notations. Sometimes it is H null hypothesis, or null hypothesis, or alternative hypothesis, which indicates with 1. So in our example, we're assuming that students drinking coffee during the exam session the same value of milliliters, so let it be 175 milliliters. If it's not true, then our mu is not equal to 175 milliliters. So when then we need to start the statistical test. There are different types of statistical tests that help us to understand whether this measure is closer to the mu that we have introduced. So here we need to introduce the alpha, which is the level of statistical significance. Level of statistical significance. And the alpha has the most widespread values equals 0.05 or 0.01. That means that we are sacrificing by 5% of samples in the first case when we have 0.05 that are situated in the extreme areas of our distribution, and 1% of our samples if alpha equals 0.01. Then we need to calculate using statistical test this value using standard error of means and finding so-called p-value. So let's call it p-value. We will see in today's seminars how we can calculate different p-values for our distributions, and then we need to compare it, calculate p-value, then compare p-value with alpha. So if p-value is greater than alpha, well, not actually the alpha, but the z-scores that we have calculated and we have studied before. So where the z-score is situated, where is our 1 minus alpha, or just alpha is situated. So let's just take alpha. If it is, this p-value is greater than the score where it's situated with the corresponding alpha, that means that we're taking, we say that our null hypothesis is true. So if it is correct, then yes, it should be true. Yes? Yes, p-value, we will elaborate it in more details in next several minutes. It's just the value which used the standard error of means and other some calculations, actually the mean of sample and the initial mu. Here's this mu, and this p-value is also shows us how much our sample is far from our population by some characteristic. How to calculate p-value, we will also discuss. Well, actually, let's start it. So in order to, well, in sometimes we will calculate not p-value, but z. In this case, it will be in the following way. So let's calculate z, but it will be very close to the z score that we have studied before. So what was the what was the z score in our distribution? Also the recap between before our today's quiz. So it is taking x value, subtract our mu, and divided by standard deviation. The z standardization makes all our values in our initial sample scaled to all this convenient z-scores, where our mu becomes equal 0 and standard deviation becomes equal 1. Here we will also calculate the z-estimate. It's called z-estimate. In our statistics. Now it will be calculated in the following way. We will just take our mean of sample that we have generated, then subtract the initial mean of our population. So M capital denotes that it is mean of sample, Greek letter mu denotes that it is the mean of population, and divide by standard error of mean. So here's the formula of z-estimate. It's a statistic or measure that is used in hypothesis testing. So let's assume that we are doing a z-test. So let's just doing here. So yeah, this z-estimates are calculated in z-test. Actually, it is our first statistical test that we will discuss. So returning to our example, let's assume that we have 100 students, random students, n equals 100. It is 100 students in our sample. We know that in the ordinary time, students drink 192 milliliters of coffee. So on average, so let's put 192, the mean of the drinked coffee by the students, milliliters of coffee. So, and we take in alpha equals 0.05. So our first step is to say that we have some null hypothesis. We want to understand whether our new sample in which our mean will equal to 175. So it's just mu equals 175. So we take, so it's the same students. So let's just repeat the procedure that we were discussed previous time. So we have our sample of students.
Big M stands for population.
Big M stands for population. Greek letter mu stands for sample. But here, we're assuming that in our sample that we have taken here after the treatment of students drinking coffee during exam session, that they have started to drink less coffee than it was in ordinary time. So here is our students when they study ordinary period. Let's just call it ordinary period. Ordinary time. So they are the same 100 students, and they drink approximately 192 milliliters of coffee. Actually, we are supposing that and the whole population of students drink this level of coffee. Then some treatment is going, so students go to the exam session. So now it is exam session. It's the same 100 students, but we don't know actually about their average level of drinking coffee. We can only make hypothesis of how many coffee they drink during the exam session. So, and let's suppose that our hypothesis that students drink 175 milliliters on average coffee in the exam session. The spoiler is that it will be not true because logically students start to drink more coffee during the exam session, but we will see how we can check this statement using statistical test. So here we have alternative hypothesis that actually students do not drink 175 milliliters of coffee. So our first step is done. Are there any questions here? Yes, Nikita? Arina, yes.
Just I guess we previously discussed that if it is each one, then is sample, so it's more group or it's vice versa.
No, you are true. Latin Greek letter M stands for population, sample, sigma Greek letter stands for population. But here, you know, in this example, there are sometimes, well, you know, it's not so much important that if you denote the sample that you have taken with the Greek letter sigma, taken mean. So it.
No, we like have M capital and
Mhm. So the idea was to differentiate the means for sample and the mean for population. So, but here in this example, yeah, in this case, you can sometimes ignore this notation instead following the fact that when we're taking the mean of sample, we are also assuming that it will be also the mean of our population. So sometimes you can see the notation that for our sample, we'll also use the Greek letter mu, and it will be okay.
Yeah, I have a question. To get the concept, so we have M capital, it's sample.
Yeah.
And if we have Greek mu, it's population.
Yeah, it's population.
And this equation, again, on this formula of Z estimate.
Mm-hmm.
Yeah, it's formula for defining where in relation to population stands each sample. And so which samples are the closest to the population? To the new population.
Yeah, let me just correct in order not to confuse you. So here we have not Greek letter mu, but just capital letter M. So we have our 100 students, and it is our sample from our population of students. So on average, they drink 192 milliliters coffee on ordinary time. But we want to understand after some treatment transformation in exam period, for example, whether the mean that represents our sample will be closer to the mean of our population. Will be there some difference between drinking coffee in ordinary and in exam period of times? So, and here, actually, yeah, we will use this formula for Z estimate. Now let's calculate it. Z estimate will be 192 minus 175. So it's the mean of our sample that was in ordinary time minus 175 of the new sample for which we make hypothesis about general population, divided by standard error of mean. So how can we calculate standard error of mean? Actually, we also have, we also have information about sigma. It's equals 15 standard deviation. So that's why we can put 15 divided by 100 square root. And the final result will be approximately 11.3. 11.3. So in this example, you shouldn't be confused by this. Shouldn't be confused by the notation m and mu. Actually, it's more important that with which type sample we are working with. Whether it is before, see my cursor, yeah? Before some treatment or some change, or it was after. So in this Greek letter M, we're taking our initial sample, so it will be mean equals 192, so it is before treatment or change. The second mean is after the change, and actually it is our hypothetical mean, so we're just pose hypothesis. We don't know actually what is the mean after the change, we just make hypothesis. And we need to calculate standard error of mean. All this stuff is given us in advance. So we know the number of students, how much coffee they drink on average before the treatment, before the change. We say that we are ready to sacrifice 5% of samples that can be very extreme ones and not good represent our data. And the standard deviation of drinking coffee equals 15. And this was also calculated for our whole population. Now we pose this hypothesis that after the change in the exam session, students drink approximately 175 milliliters coffee on average. Alternative hypothesis that it's not true. We need to calculate Z score, not Z score, Z estimate by this formula, and we have taken this value 11.3. In the next step, we will see, we will compare with a score that will show us that can we take the hypothesis as true or it is false. But are there any questions right now? Yes, Alexander?
So data given to us leads people to understand
Here?
the significance from the example we projects calculated. So if we have Z estimate, alpha, mu, etc., we can calculate even from Z.
Yep, p-value, well, actually in this...
If I understand correctly, to understand the significance of this hypothesis, hypothesis, we need to understand the p-value.
Well, yeah, p-value. Actually, p-value is some general meaning, and in this case, p-value. Thank you for your question. Actually, so you don't see it. Actually, one of example of this p-value is a Z estimate that we have just calculated. There will be another estimates that we will calculate. And one of this example is Z estimate of p-value. P-value, it's like precision or some other measure that help us to understand whether our sample is significant and represents our population in a good manner. So we just need to do the last step in this example. So we have calculated our Z estimate. It's equals approximately 11.3. 11.3. We know that for alpha, so it's just statistical fact that for alpha equals 0.05, we have Z score equals plus minus 1.96. So that means that for alpha equals, so let's just not to confuse you. So it will be minus 1.96 for alpha equals 0.5. But you know, in our distribution, we also have another tail. So here's our Z standardized distribution. So let's see, here we have mu equals 0. Mu equals 0. We have calculated on the left and on the right, find this Z score equals minus 1.96, and here it will be Z equals 0.96. So for alpha, so let's call it alpha minus region, it is alpha plus region, 1 minus 0.05, it is 0.95. It's a 95th percentile on our distribution. So here it will be plus 190.96. We have found this information from our statistical tables. So it is Z scores alpha. Actually, there will be also every time given. Here it's this statistical tables that have already been calculated by statisticians. And we know that for alpha equals 0.05 and Z minus 1.9. So we take this concrete intersection. It is approximately 2.5% is situated in our data. And it is exactly what we have done. So we have 95% here in this region, in our central part of distribution. And here we have 2.5% in this extreme area of samples that can appear very rare, and here 2.5%. So once again, that's why this standardization of distribution was very important for us, and we will just write the quiz on it. We have construct this standardized distribution of our sample, and we see that if we take alpha equals 0.05, that means that 5% of data goes to these two extreme regions divided by 2. So 2.5% goes on the left tail, the last part, and all other points in the right tail, 2.5%. The problem is to calculate these concrete values where they are situated, but the statisticians have already done it for us. So it's calculated in this, have been calculated. And now we just need to compare the Z estimate. So our estimate 11.3 is situated here. Actually, it's very high. So our Z estimate 11.3 greater than 1.96. So that means our null hypothesis is not true, so we derive our conclusion. So it is not true, is not true. That means our alternative hypothesis is true. Yeah.
The first one is why do you draw, you know, what is the logic of if d is 0.05? For sure that is -1. Why do you draw an arrow?
So alpha, you can represent it in the following way. Alpha that we have introduced here equals 0.05 means that there are 5% of sample that estimates that can be extreme ones. We're assuming that our distribution of drinking coffee is a normal distribution, and when we take 5% of extreme values, where they can be put? They can be put on the left extreme region and in the right extreme region. We also standardized our distribution, and it is symmetrical one. That's why we can be sure that equal parts of 5% will be put in the left and the right extreme tails. So that means that will be 2.5% and 2.5% here. For example, if alpha were equal to 0.01, then just 0.5% or in the left. Yeah.
The question is, how is the relation between alpha and z defined? If this opens the table of alpha z, how can more than one z stand for alpha? I don't understand. If we have this idea that z is, for example, always like 97. If z 97% of distribution is like between z equals this and that equals z equals -3, for example, that equals 3, and this general symmetric distribution. This means that this z would for sure connect to alpha equal 0.03, but it is not for sure. Why is it? How can more than that one of
Yeah, I see what you are driving at, Nikita. So thank you that you have raised this question. Actually, we are starting, looking not on the z-score. It was my mistake to tell you this. We're looking at the how many percentage of data we want to put in the extreme areas. So we have assumed that we take alpha equals 0.05, then we go through our columns. For example, here it says that 48% of data can be put in extreme values. So it's just a very high value. Here is just z-score equals 0.
what is z-score?
It's our standardized
if alpha is 0.5,
it's our
47% of z-score 0 will be in the triangles, and
it's our standardized distribution of samples means. So we have started today's lecture with calculating the following example, that we can construct all possible samples from our initial population. Now let's go to the example of students. Suppose we have population of 50,000 students at HSC, and we need to take 100 student sample from this whole population. The size of such samples will be enormous. How many ways we can construct 100 students? Yeah, it will be an enormous number. And we will can calculate the means of all these students hypothetically and construct this distribution of samples means, but of course we won't do it. It's very expensive and very long procedure. We don't have so much time, and nobody paid us for this monkey job. So actually standard error of mean help us to to be used in order to scale on our sample, because it's important what's the size of your sample. If it is small, then your standard error of mean will be higher, because the more data you have in every task in your life, the more significant conclusions you may rise. So that's why we also depend on the size of our sample. And why we need to take the standardized distribution? Actually, this z-test that we are doing here, why it's called a z-test, we transform all our data to the z distribution. So let's assume that we scaled our initial also sample to the mean of sample to the z distribution of samples means. That's why we calculate this z estimate, which is very close to the calculating z score. But here we calculate it not from x, but from mean.
Here for this formula, so that is really a question that I don't understand. What does it even mean? Because you see, if we're speaking about mean of sample minus mean of the relation, we have to get some value in relation to the generally understood standard deviation. I understood correctly. But sigma of the mean refers to the standard deviation not between means, but within one mean. I probably come after
No, no, it's a very good question, and I think that nobody understands what's going right now. That's why we need to elaborate about it more. So M, we have calculated for the particular sample of our students. So it's just one sample, 100 students, and their particular mean equals 192. So, we know from previous experiments that this sample represents, well, our population of students that are drinking coffee during ordinary time. Then we change, something has changed with our sample, and it's the most valuable part in every analysis. And we need to understand whether this change was significant or not. How can we do it? We need to pose hypotheses about our statistical measures. That's why in statistics, this means and standard deviations are so important, because they describe our data distributions. We don't have any other such measures or characteristics that better describe our distribution. They are only mean and standard deviation. Not only them, but also some other. That's why in this z-test, we will use the mean of a sample that will relate to our whole population. That's why we can also denote it with mu and not with capital M. We just want to, this hypothesis is rather primitive one, because we comparing with the exact number, just with 175, and maybe we will be right or we will be wrong. So, but actually in our course, we will not take some other things. There will be always with means equals some number. So then we calculate the z estimate, 11.3, it will be equal. And now we have calculated for this particular mean that we have, we subtract from our mean from ordinary time and from the hypothetical mean divided by standard error of mean for this particular sample and take to actually one measure, 0.05. And we're assuming that 5% of data, 5% of samples means that we have taken from our experiment may be unlucky or just extreme values that are not good to represent our data. And finally, we compare it with this value that we have taken from this table. So we find that 0.05 alpha, we are going to take 5% of data. So it's actually not 5%, but 2.5%, or it is 0.025. There is no concrete number because it is go with the 0.1 step for z-score. So, but it is approximately, well, actually should be -2, but we'll take -1.96. But we don't need to do it. It's already an unknown fact. And it's always also taken in some conditions of the tasks, that for alpha equals 0.05, it will be plus minus 1.96 for z-scores. And then we compare our z estimate with the z-score. If it is greater than z-score, then our null hypothesis is not true. Otherwise, if our z estimate were less or equal, well, about equal, it's discussable. If it is less than our z-score that we have chosen, then our hypothesis was true, then our hypothesis, and indeed our sample that we have seen after the change represents with not sufficient error our population.
We have to prove it right.
Sorry?
So I think the theory is right.
If our estimate equals 0 or less than 1.96, then yes, our null hypothesis will be true. Or if it was -1, it will be also true, because we compare not just with only 1.96, we compare with this region. So by absolute value module, if it is less than 1.96, then it is true. Yes, Vasily?
It's about formula, because you got two formulas. When the z equals to x minus mu divided by sigma, and the formula when z equals to m capital minus mu divided by sigma m. Actually, yes.
So, and the question is, what's the difference?
Yes.
So the first formula is just the recap, how we can scale our sample to the standardized distribution. Why the standardized distribution is so amazing? Because it has the mean equals 0 and the standard deviation equals 1. And if we standardize all our samples from the same population, they will also be scaled to these values where our mean equals 0 and standard deviation equals 1. 1 plus minus 1, depending on which direction we will go through this distribution. In this example, we can compare our values that we're taking with from another sample. This formula for z estimate, it's the particular formula of our first statistical test that we have discussed today, z-test. And it goes here. The difference is that instead of standard deviation that we divide it by standard error of mean. And instead of x value, we take not just x value, we just take our particular mean that has our sample before the change. Okay, thank you. So actually, very in shortness of time, there was some question about quiz. Actually, the last part of this quiz. Let me just see the question. Was it the 6th question, Polina? Yeah. So let's see z-score. A great question. So actually, the answer was here. Z-score.
It's about the cost.
Graphs. Okay, great. Here. Okay. So the question is that we have two different distributions, different means, and we need to scale them or not to scale.
We just need to use a formula.
It's just like we had to standardize it according to the format.
Yeah, you need to standardize the first distribution and the second distribution. And then when you standardize these distributions, then you will find that for a value where it was x equals 76, here you see this standard deviation equals 12. It is rather large. In this particular distribution, you actually also can see that it will have a higher z-score than in distribution. Not just calculate. Actually, you may not calculate. You just look at the sigmas. So where the sigma standard deviation is higher, and also you see that this 76, it will be. Well, you see this x equals 76 after standardization will have z-score equals 2. Why? Because two sigmas are placing between 70 and 76 in standardized distribution. Here we have 76, so it means that, yeah, actually this correct answer, yeah, that here it will have 0.5 z-score. Why? Because 76 minus 70 equals 6, 12 divided by 6, 6 divided by 12, it is 0.5, so that means it is less, and the correct answer is that the z-score for A graph is higher than for the B graph. Okay, now I suppose that we can start. The link to the quiz I have sent to the Telegram chat. Also, you can find it in our Edu HSE course page. I'm just, yeah, right now it is opened. Just refresh the page and good luck. Please, when you finish, you can just go to have a rest. It's called quiz 3. It's in the quizzes section, the very first element. Quiz 3. And then we will go to the seminar and try to understand. Yeah, now we have given you some statement, ethical statement, in order to be more conscious about what you are going to do.
Just mock quiz 3?
Yeah, just quiz 3.
Just
quiz 3, not mock quiz. It will be not graded. It was just a hint for you to prepare for today and to understand what's to do. So yeah, you have 10 minutes. There are 6 questions. Totally, you can achieve 12 points. That means that you can have one mistake and you will also have the highest grade. So it's just for you to make more chance to get higher grades. But maximum will be